Thanks for the introduction, Alexei, and thanks for inviting me here. So I'm Jiang. I'm a bit of introduction of myself. I'm leading the ecosystem integrations and developer relations at Zilliz. For folks that don't know, like we are actually the creator of the open source vector database called Milvus. I know we have two names, so that is always confusing. But we are the company who are still the major maintainer of the Milvus project. The Milvus project itself has been donated to Linux Foundation Data and AI. So the QR code is my LinkedIn. If you want to connect to me in person, we can talk more there. Today I want to share more about the advancement in RAG. As most people have known, like RAG has been really widely adopted in those AI applications. However, people are constantly frustrated by the quality problem of RAG. Because a naive RAG, it is impressive, but it doesn't solve all of the problem. So actually, I came from the search, indexing, and infrastructure background. Back in the days when I was building image and video search at Google, we actually heavily depend on two pieces of technology to improve the retrieval quality of the search system. One is the deep neural network and the vector embeddings, which has been known by many people already. The other one is actually KG, a knowledge graph. So there is a lot of things in knowledge engineering regarding like how do you systematically extract the knowledge information from the unstructured data from the, say, web data corpus, and then organize them in a systematic way so that during serving time, like online serving time, you can effectively retrieve and leverage the information behind that. Because, you know, for just look at how like human beings are encoding the information, right? We have the human language, which is a great tool, but the human language usually talks about things together rather than giving it a structured representation. So that having vector embedding that can help us retrieve the raw text from the, say, web pages or internal documentations, but it doesn't really solve all of the problem because sometimes we still need some structured way to encode the information so that you understand, you know, we can help machine to understand the relationship between the knowledge entities or the relationship between the concepts. So that's a great enhancement to RAG, to see this difference in action. So here is a graph from the paper which does the survey of the you know, LLM-based chat and RAG-based, and also KG plus RAG-based. So as you can see that, you know, simply using LLM, you are pretty much relying on the sole kind of essential capability of the large language model itself, which was not trained on your data. So that adding LLM with the retrieval or like vector search, you can leverage your internal documentation, like things not like information not available to the public or to the public data sets where the large language model was trained on. However, with only this, you're pretty much relying on the combination of information applied in those raw text. Say, if I have a text chunk talking about like concept A and B, and then if I was asking about what's the relation between concept A and B, and then you got lucky, it will be very trivial to retrieve those content. However, if I have a complex set of relations between a large set of like entities or like things I care about, in that case, like we just don't have enough data corpus or enough text from those documentations which talks about every single aspect of the things. So that a systematic way of tackling this problem is actually using the knowledge graph to extract those information, to establish the connection between those individual concepts, and then together we build a graph. And you know, this graph can be as complex as the right. or it could be as simple as the left. Well, it depends on how the amount of information that your application wants to leverage. Say if you have simple just graph architecture, then in that case you can just use this as is, which is already a good way of encoding those information. However, if you have a very complex set of entities and relations between them, you can further apply data mining techniques by having you can do clustering of the knowledge entities, and you can extract summary out of it. You can even as the GraphRag project published by Microsoft, you can even establish the layered structure of the summaries, or they call the communities. Like with this kind of technique, there's just unlimited ways of extracting the essence of the information from your documents, from your document corpus. With this idea, one of my favorite work on this in this domain is called HippoRag. So this research actually tries to combine the vector embedding based retrieval, which is pretty much just semantic search of the raw document chunks, whatever you have, and then combine it with the mined information stored in the knowledge graph. And then in this work, it does some fancy stuff on the graph retrieval, which is for each query, it actually it first finds what's the most related entity from this graph to my query. And then from this starting point, it actually runs a PageRank, a so-called personalized PageRank algorithm to kind of to flow the information through the relations and entities and this structured representation. And then with this, just like how PageRank in traditional web search helps you find the useful information, it uses this algorithm with the same intuition to find the information and could potentially help your query. However, this is really expensive because it happens every time for the for each query you need to run another PageRank, and PageRank is no cheap algorithm. So inspired by this, we actually did some experimentation and figured a relatively straightforward but very effective approach of combining the the power of knowledge graph and vector search in this RAG use case. So how it works? So just like as any search system, you need offline indexing phase and online retrieval phase. So for the offline processing, it actually analyze the corpus, just like how you do a so-called conventional RAG. I mean, it has just been here for I think less than 24 months, but it has been conventional. So as the traditional RAG does, it does the chunking of the documents from your data corpus. However, on top of this, it also uses large language model to extract the entities and relationships out of it. Well, you can store it in a graph database like Neo4j and then do further mining of this and extract more information. So with this analyzed and structured information, you can do so-called knowledge embedding of the knowledge entities and relationships, and then store those embedding, those vector representation in a vector database like Milvus. And then you can continue this retrieval approach with a slightly enhanced approach, which I will cover a bit in detail in a bit. So the first problem we need to tackle is after we have the knowledge entities and relationships extracted from those knowledge graph, how do we actually encode them into vector embeddings? Well, just like the way of encoding raw text or image and video and other any unstructured data, we can actually apply a very simple approach, which is to represent the relation, the triple of two entities and one relation into just a plain piece of text. And then with this text, you can use any text embedding model to encode it into vector. This well, just contrary to our expectation, this actually works pretty good in practice. Once you have this, you can go through a slightly more complex flow of retrieval at the online serving time. So given the query, we find the most adjacent entities and relationships from the vector database, and then with this, we really want to leverage the power of the graph, so that instead of just using this, we'll actually expand the node into its adjacent subgraphs, and with this, we can re-rank it by large language model to actually filter those things that are not really relevant to your search query. Because by expanding it into subgraph, you may encounter things that are totally unrelated to your query, despite the kind of origin entity was related to your query. And then with this re-ranked relationships, we will get the metadata, which are the passages where those entities and relations were extracted. And then this will be the final data used for large language model generation. You can put them into your prompt and maybe use despy to optimize that prompt. So to see this in action, we actually constructed two tables. One is the relation table, which contains the text representation of the knowledge triple, like source entity, relation, and destination entity. And then we do have the entity table as well, which has the text representation of the entity, which is pretty much the name of the entity. And in addition to this, we have vector embedding of either the entity or the relation. And we also have other metadata fields so that it can help you to, for example, get the raw text out where this entity or relationship was extracted from, and the related entities, so that if you are just doing, say, one hop of retrieval, you can just directly use this data. So here's how it works in terms of expansion, finding the subgraph, and large language model-based re-ranking. So first of all, we encode the query into a vector embedding, and then search this vector embedding in both of the tables with their related entities and relationships. And here the dot denotes the entity, and the edge is actually a relationship. With this, we want to expand it a bit further so that we can know this will help us solve the multi-hop problem. So we do this by a brute force approach. We just expand to everything adjacent to it, limited by the number of hops. Say if we do this by 1 degree and then we just expand once. If we want to do it by 2 degree, probably you will get one order of magnitude more data, but that's okay. We'll see in the next step, we'll actually merge those retrieval results and then re-rank them by large language model. So let's say here we have retrieved maybe 30 relationships and entities. That might be too many for us to get their original raw text chunks and then stuff them into the large language model's prompt, because that will just burn your tokens. So instead of doing that, we'll actually do a large language model based re-ranking by carefully crafting a prompt, which pretty much just says, here is the question I want to solve. In this case, I was fascinated by the Crusade kind of history. So who is the mother of the leader of the Third Crusade? And when was his or her mother born? And in this case, it actually has a quite a few hops of information needed in order to answer this question. And what's listed behind this question are all of the, here in this case, relationships that we have retrieved before. Because if there was anything from the document corpus that can help it, it's very likely that those information are spread across the graph. And the information are not spread across very distant from each other. They will be related. I mean, this is just a plain observation of how human, like how we organize our knowledge is. So with this intuition, we know that, well, from this list, there will be probably enough information to answer this, or otherwise you just simply don't have this information from your document corpus, then nothing can help other than you kind of construct those documentations, which is also a very useful technique to improve the retrieval quality, even though it sounds like a bit too plain. That being said, with those relations, you can see like some of the information are not really related to or not helpful to answering this question. However, there are some. In this case, the large language model uses it basically just think out loud. So it's very helpful to force the large language model to speak out loud regarding its thought process. So in this case, we use this prompt technique, and it actually explains, okay, to find the answer of this question, I need to reason about the relation between those concepts. And the result of that reasoning is that it figured 3 pieces of information. In this case, those are relationships from this knowledge graph, where the Richard the Lionheart actually led the Third Crusade, and who is the mother of Richard, and like this woman was born in which year. So with this, we're really close to solving this whole problem. But just one last piece. There's actually another research that analyzed the effect of, the results of solely using the text representation of the knowledge entities and relations versus directly using the raw document chunks from your data corpus. I mean, apparently, if you are using the document chunks, you're consuming more tokens in the large language model inference phase. But this is actually useful because, remember, we actually used large language model or a mechanical way to extract the knowledge entities. This is not always reliable. I mean, it works pretty well in practice, but it's not always reliable, especially compared to having human beings annotating this by hand, annotating or constructing the knowledge graph by just looking at the text. You can hire a lot of laborers to do this, but that will be pretty expensive. So with this compromise, it's actually very meaningful to directly use the raw passage where you extracted those entities. Well, you can also you can do more by stuffing the text representation of the entities there as well. We didn't test this, but I think it could provide a little bit of help, but maybe it's not worth the extra hassle because with those raw text chunks, you already have enough materials to cover those information represented by the knowledge graph, by the entities from the knowledge graph. So let's look at the final result. We compare this with both naive RAG and which is the blue bars, which is the green bar, and HippoRAG, which use the personalized PageRank algorithm, where for each query you need to anchor on a node and then run the it's kind of a walkthrough or traversal algorithm through the whole subgraph or even the entire graph. So compared to that, the straightforward approach of using only knowledge embedding vectors for retrieval in the online serving phase actually does better than both HippoRAG and naive RAG. So if you would like to check more, if you would like to have more fun and play with this approach by yourself, we actually have the open source Milvus that supports all of the deployment modes, from as simple as installing Milvus Lite in your laptop or notebook by just pip install, to very performant and scalable Docker and Kubernetes deployment. And also, if you are using the, if you favor using API service, we also have Zilliz Cloud, which is managed Milvus by us, and we provide both serverless and dedicated instance for you to get started with. And the Milvus project, because both the self-deployed Milvus and the commercial Zilliz Cloud offering, they share the same API, so that you pretty much just need to develop the application logic once, and then you can use it anywhere with whatever environment. And they all work with a whole lot of frameworks in the RAG and AI application development space, including DSpy and other projects. So that's all from my sharing. So if you like to check more about Milvus, here's the QR code for our GitHub page, and we also have the Zilliz Cloud, the fully managed Milvus as a SaaS offering. So if you are interested in this kind of work, like tutorials and best practices in applying vector search in your GenAI applications, we have more tutorials and demonstrations from Milvus.io. We have, multi-modal RAG, graph RAG, and other like hybrid search. All those examples that will be, helpful in if you are exploring the semantic search space. So that's it. Ready for questions?
So we're a bit out of time, but I think it's great. Also, let's have a couple of questions. Okay, next question.
Yeah, there are actually more complex ways of creating embeddings for knowledge entities. For example, there are approaches where they encode the subjects, the entities, and the relations, and then with even the doc chunks where those entities were extracted from. We tried that, but one interesting observation is that, just simply using the text representation, just concatenating the names of the entities and relations, that works pretty well in practice. In terms of beating the both the traditional RAG and personalized PageRank based graph plus KG plus RAG approach. That's one thing. So this approach is more reliable and more widely available because there are just tens of text embedding models, but there are not as many knowledge entity embedding models. On the other hand, we observed improvement on the overall search quality by simply upgrading the embedding model, the text embedding model, from a smaller one to a larger one. So that if that's really the approach, the direction of optimization you want to go after, just simply using more advanced, more recent embedding models can provide sizable improvements in terms of the summarized score of the retrieval quality, at least evaluated by those public data sets. So I think definitely there is, we do have interest, and I think there is a need to explore more advanced graph embedding techniques. But in this case, there are also other places to optimize, such as the performance and latency of the retrieval approach, because it does involve large language model as part of the retrieval, which is used for re-ranking. And also, we tried expanding it beyond 2 hops. Like we tried expanding to 3 and 4 hops, and then doing a trimming of the things retrieved from that without using large language model. And we found interesting results that simply doing 2 hop of retrieval that gives you a good enough results, and expanding towards say 3 to 4 hops, it doesn't really help that much. So I think like those kind of optimizations are maybe they are more like cost effective than exploring the knowledge embedding, because the current landscape of embedding models are like most of the embedding models, they are based on BERT or large language model architecture, and some even if you can invent a embedding model architecture that kind of optimized for the knowledge entities, if there's not enough attention from the community and from the industry, you don't have enough good training data to improve its performance, it's very likely that it cannot still compete with this very simple approach.
Thank you very much, John. Really appreciate it.
Thanks.